Hello all, it's Andrew Engineer for the second part of the design of our reinforced concrete beam. Okay, so here now we are going to enter more into detail. The first part we have to see the various conditions to know before to verify before even calculate the area of our steel. Okay, so now we are going to further our calculation or our research. Now we have been given the M ultimate already. Okay, then we have the FC28, the characteristic strength of our concrete after 28 days, the elasticity of our steel, that's 400 megapascal. The section of our beam or the cross section of our beam remain the same. Okay, yeah. So now we'll quickly calculate the mu ultimate. Okay, mu ultimate will be equal to what? We already know the formula: M ultimate divided by BD square sigma GC. Okay, the design strength of the concrete. In this scenario, the design strength of our concrete will be equal to what? We have calculated it already. We know that it's equal to 0.85 FC28 divided by gamma C, okay, for concrete. So it's equal to 14.16 megapascal. The previous video we make the computation, so we already have the value. Okay, so that's the design strength of our concrete. Okay, so for D is the same. D is equal to 0.9 H. Okay, so we have made the numerical application. We came out with 36 centimeter. So we have D, we have M, we have sigma DC. So we can go to the numerical application for our mu ultimate. Okay, mu ultimate will be then equal to what? It will be equal to 3.61 times 10 to the power negative 3. For the sake of conversion, I will multiply it times 10 to the power 3 first of all to convert the meter into millimeter, and times 10 to the power 6 to convert the meganewton into, because you can see here it's in meganewton meter, to convert the meganewton into newton. Okay, so now divide by what? B, the base of our beam, which is 20, convert into millimeter, 200. The D, which is 360. Okay, 360 square. Okay, sigma GC, which is 14.616. Okay, so that's it. Now we punch 3.61, okay, times 10 to the power negative 3 times 10 to the power 3 times 10 to the power 6. Okay, you have this. Then we divide by 200 times 360 square. Okay, don't forget the square, times 14.16. okay, we have 9.8 times 10 to the power negative 3, which is simply equal to 0.0098. okay, we can round it up. We can simply say that it's simply equal to 0.01. okay, so we'll take the 0.01. okay, so from here, when you compare now mu ultimate, we realize that mu ultimate is less than 0.186. okay, which implies that we are in pivot A. okay, for those who are new on this video, you can go back to the previous video. You will see how we actually obtain how we make the differentiation, or we classify the various pivot A, pivot B, pivot C. I will leave a screenshot of the link of this video in the just up. okay, you just look up and then you go and check it. So this is it. We are in pivot A since our mu ultimate is 0.01. What we do next is what? We calculate alpha ultimate. okay, we calculate this coefficient, which is equal to 1.25 factors of 1 minus square root of 1 minus 2 mu ultimate. okay, we'll make this computation quickly. We have 1.25 factors of 1 minus square root of 1 minus 2 times 0.01 okay. Numerical application will obtain how many? So we'll punch it times in bracket 1 minus square root of 1 minus, no, first of all put the bracket 1 minus 2 times 0.01, okay, we close the bracket, okay, close it, is equal to 0.012, okay. So our alpha ultimate is 0.012, okay. We obtain alpha ultimate. What is the use of alpha ultimate? Alpha ultimate will actually, in other words, help us to calculate what we call z, okay. So now we fall into the calculation of our z. Z is equal to what? D factors of 1 minus 0.4 alpha ultimate, okay. That's how we obtain our z, okay. In numerical application, we'll have d, which is, I will leave it in centimeter here, minus 0.4 times 0.012, okay. 0.012, which is here our alpha ultimate, you have 36 times in bracket 1 minus 0.4 times 0.012, okay. You have 35.82. 35.82. I will leave it to be 35.8, okay. This is our z. So when we have this z now, we can actually compute the area of our steel, okay. The area of our steel, this AST, which is equal to what? Which is equal to our M ultimate divided by Z sigma YD. Okay, sigma YD, which represent the design strength of steel, okay, the design strength of steel which we are to compute, okay. So we can erase this place or this part. Why erasing? Now you can say that the design strength of our steel is equal to what? The elastic strength of our steel, that's 400 megapascal, divided by gamma s, which is the safety coefficient, the coefficient of safety of the steel. In numerical application, we'll have design strength of the steel is equal to what? Is equal to 400 megapascal divided by 101.15, okay. The coefficient of safety here is equal to 1.15 for the steel, okay. So we'll have to punch the value quickly. We have 400 divided by 1.15 is equal to 347.8. 347.8, okay, 0.82 for 0.8, okay. We'll take one decimal places, okay. So this is the design strength of our steel, sigma YD. Now we have the design strength of our steel, we have Z, okay. We have also our M ultimate. So what else? We just have to calculate our AST. So AST in numerical application 2 point, okay. AST here will be equal to what? It will be equal to M ultimate 3.61 times 10 to the power 6 directly. We have converted in millimeter as the previous case. We convert also 358 in millimeter, this rate, okay, times what? Times 347.8, okay. The design strength of steel. So numerical, why? When we punch it, we punch times 10 to the power 6, okay, divide by 358 times 347.8, okay. We obtain 28.99. So 28.99 is in millimeter square, okay. This the area of the steel. For the tension area, remember we are in pivot A, so we actually try to reinforce our beam actually in the tension area. You can see here, okay. So we'll calculate the AST mean, because AST final, which I will abbreviate AST final, ASTF, is actually equal to the maximum in between AST, okay, AST and AST mean. Okay, so we'll have to check the condition on non-fungibility, okay, the condition of non-fungibility to have the AST mean. So AST mean will be equal to what? AST mean, let me just erase this field. Our AST mean will be equal to 0.323 BD, okay, times FT28, which is the design strain, which is the strain, okay, the strain of our concrete in tension, okay, the tension strain of our concrete divided by Fe, the elastic strain of our steel, okay. In numerical, so we have an unknown, that's FT28, which represent the strain of our concrete in tension, which is simply obtained by calculating 0.6 plus 0.006 FC 2028. Why doing this? Okay, times 25 megapascal. Okay, the characteristic strain of our concrete after 28 days. To have also the characteristic strain of our concrete in tension, because here it was in compression. So numerical wire punch will obtain 2.1 megapascal. Okay, you obtain 2.1 megapascal. You can verify it with your calculator. So now we have our FT28. Okay, so we can find the AST mean in numerical application. Okay, AST mean will be equal to what? It will be equal to 0.23. This is according to BIEL. Okay, let me just, as a reminder, we are working with the BIEL code. Okay, times, I convert again in millimeter. BD, D is what? 360, if I'm not mistaken. Okay, 360 times 2.1, okay, divided by 400. Okay, so here we'll have what? 0.23 times 200 times 360 times 2.1 divided by 400, 86.94 millimeter square. Okay, this AST mean. Okay, so now we can quickly compare our AST mean with our AST calculated. Okay, and we remember the AST final, which is the one that we are going to use or implement on site, okay, is the maximum in between AST calculate here and AST mean. So simply cross-checking the two answers, we can realize that AST mean is greater than AST. So the AST final that we are going to use, okay, that's the area of steel in tension that we are going to use, will be simply equal to what? Will be simply equal to 86.94 millimeter square. Okay, it's a section, it's an area, so it's in millimeter square. So when you reach here, you can say you are done with your design, because what is left is just to determine the diameter of your reinforcement, the diameter of your steel bar according to their geographical area, maybe. Okay, diameter of your reinforcement and the number of reinforcement. Remember, you are in pivot A, so we are trying to reinforce only in tension area. Okay, so here let me just erase this. You use like a bonus, you just use this formula. AST is equal to NP diameter square all over 4. This formula will actually enable you to have to choose the diameter of your reinforcement, and from there to obtain the number. This N will represent the number of reinforcement of that diameter that you have chosen. So if, for example, you put diameter to be 10 millimeter of diameter, then you come down here, you take your AST, you substitute it here, you will be able to come out with the number N of diameter 10 millimeter of reinforcement needed for that tension area. Okay, if you have learned, I think we'll stop here. So if you have learned something new, okay, if you are new on the channel, don't forget to subscribe, okay, to activate the notification button, okay. Share our video, like, leave a comment, even to encourage the channel. If you have any question, leave it in the section of comment too. Thank you so much. It was Energy Engineer.